Here we are looking at optics, the dynamics, preamble. Let's set the problem up. Here's the medium 1. Here's medium 2. The boundary is at x is equal to 0. We have an incoming wavefront of electric and magnetic fields. It's reflected. There it is. And we know from the previous kinematic studies that theta I equals theta R, billiard ball reflection. And we know what theta T is from Snell's law. So we know that N1, if N1 is the index of refraction of material 1, N2 for material 2, N1 sine theta I is equal to N2 sine theta T for transmit. And the point is that we already have this kinematic information. We don't have to redo it. We will find that this comes up in the dynamics. So what do we mean about dynamics? Well, we want to now actually calculate the amplitudes of the reflected and transmitted fields. And in order to do that, there are two things we need. One is we have to be able to represent the plane wave for the electric and magnetic fields. And we're going to do that starting with the incident plane wave. And then we have to figure out how much of that amplitude is associated with reflection and how much of it is associated with transmission. To do that, we have to do something called boundary condition matching. And we'll look at that in more detail. But before we get into the details of the boundary conditions, I want to represent each of the waves in terms of what we know as exponentials and give us a bulletproof way of doing this. So we'll never get confused about plus signs and minus signs. And that relates to previous work we've done in class.